Hi, my name is Janelyn. This is my dad, Randy. I hope you all are doing well over there in Worcester. A team we are part of is Dirt Team 2040, the Dunlop Eagles robotics team, which is in central Illinois. This presentation is about how we use code generation in MATLAB Simulink for programming in the FRC season. So, some quick introductions. I was a student in Dirt 2040 starting in fall of 2021 and graduated in 2024. Even though I'm not on the team and can't be a mentor for a while based on the team's rules, I can still help out every once in a while and keep the C++ framework updated. I'm enrolled at Illinois Central College, but I'm transferring to the University of Illinois at Urbana-Champaign next year. I'm currently majoring in systems engineering and design, and here's my dad.
Hi, I'm Randy Anderson. I'm a mentor with Dirt Team 2040, Dunlop Eagles robotics team. I've been a mentor since 2023. I work at Caterpillar in Peoria, Illinois, where I'm a senior engineering specialist working on control systems. From education, I got my mechanical engineering degree, Bachelor of Science in 2000, and a master's degree in 2005. All right, so why did we do this, MATLAB Simulink code generation process? So I joined the team and I was helping out with electrical for the 2023 season, but other people were doing programming. So the next season, we lost a lead programming student and mentor. So I was the only programming mentor for that season in 2024. And my only coding experience was with MATLAB Simulink from my work at Caterpillar and a previous employer, and even further back in college. So, and furthermore, controls engineers, in many fields use Simulink for controls design and simulation, as well as, automatic code generation. So this is a good tool for students to learn if they're interested in control systems or robotics. And because, in my work, I would do programming in MATLAB Simulink, and other people figured out how to integrate that generated code into the embedded processor. So I challenged Janelyn to find a way to incorporate the Simulink generated code into the FRC software framework.
The framework I ended up with after some revision was this, and we'll go deeper into some of these sections, but at a high level, remember that the block code in MATLAB and Simulink generates C code, and the hand code is the C++ code written with WPI-lib that interfaces with the generated code. All that makes the final robot code here. So this is a simple little snippet of Simulink code. As you can see here, the subsystem in the middle is basically a function, and the imports act as the arguments, and the outputs act as the return statement. These blocks in the middle edit the data carried by the signals. Basic block coding, but I want to be clear in terms as we get into more complicated topics. All of the programming we do in Simulink is functional programming, though. Simulink also has another tool inside of it as well. It's called Stateflow. Stateflow is a block coding state machine tool. These state machines are encapsulated in charts, which, as you can see on the edge of the screen, interact with Simulink as well. We usually have at least two of these. The first one is for autonomous routine. The second one is usually some sort of chart that tracks the position of the game piece in the robot and how to move that game piece. As you can see, we have states and transitions between them. Inside of those states, we can edit output values, run small timers for time transitions, like switching between red and yellow, and transition based on inputs to the chart, like button inputs. This is very useful for being able to change state machine logic quickly when things are going wrong in a regional. Here we can see the entire model for Dirt's Reefscape season. The inputs and output stages are kind of self-explanatory. They encompass all the imports and outputs for the model. Black vertical lines you see everywhere are bus creator and bus selectors. Buses are the solution to not having a ton of single lines everywhere. They condense signals into one signal, a bus signal, where you can then use selectors to take that signal out wherever you want. The pre-processing stage has a couple sections in it. The top three, steer module offset adjustments, odometry, and position Kalman filter, are all for calculating the position of the robot on the field. The HID's processing does Things like adding deadbands to joysticks, debounce, and rising edge detection for buttons, because we pass all the joystick inputs in raw. The last two are season specific. We'll talk about the limelight tag corrections in the next slide, but the rescape sensor processing subsystem resets the 0 point for the elevator using limit switches. The game state logic is made up of 4 conditional subsystems, meaning that only one of them runs at a time based on what game state the robot is in. Next is post-processing. Spline path following is a custom spline following function that follows a Catmull-ROM spline that can drive the robot. We have a tool to simulate the travel of the robot for creating the control points. The autonomous game state logic picks which path segment to run as well. The swerve drive subsystem is like a regular swerve drive calculation object from a C++ library, but custom and has some issues. It's great. And then the rescape subsystems, all of them do some sort of closed loop control to make the motor DCs for the elevator, coral arm, and endgame lifter. As you can see, we also have a large and small subsystem we'll show the insides of next. This is the inside of the small subsystem. Here we just turn meters into inches and add a configurable offset for fudging if needed. Those codes then go on to be processed more later. Simple. This is a large subsystem with a bunch of nested subsystems, and we have a little video just to show you the scale of this block. So that's kind of how the Simulink works at a high level, but how do we integrate this with the C++ code and WPILib? It's through the build script. The inbuilt Simulink coder generates the C code with some settings changed in the configuration, with an additional build script. This build script assembles 2 files, a CPP and an H file, which contain network tables code generated from the Simulink model that put in tunable parameters, numbers like PID constants, fudge factors, and such, top-level imports and outports, and test points, print statements you can attach to any signal, into network tables. Tunable parameters are like numbers you can edit in a program like Glass or Smart Dashboard. Then Simulink will use those values live, while test points and top-level ports just display their values over network tables. To make the C++ not need constant upkeep, we use a made-up thing called a component. When the class component is inherited, it makes the programmer create a pre-step and post-step function for the child class. When instantiated, these objects are pushed back to a dynamic array and called every 20 milliseconds in the robot's periodic. This means that there is no connection of components directly, and they can be run in any order. Components only interact with Simulink interface and robot.h when they are instantiated. From now on, I want to be clear, if I say component later in this presentation, I mean any class that inherits the class called component. Just want to be clear with that. But we can go a step further. When I was on the team and someone would come into the shop for a day or two, I would sometimes try and talk them through creating a motor for their first bit of code to do. But when I did that, it was actually very hard for them to get started with tons of docs to learn. So I decided to make a motor wrapper. I also did this because some vendors, Rev Robotics, seem to like to change function and object names frequently, and they always break all my code. So I'm going to show you here how to make motors with create info. I took heavy inspiration from Vulkan, a C library, to structure this. Every motor has their own create info. As you can see, can ID, the default direction, current limits, and more are all configurable. You might also see we have some pointers here. Those arguments are, with ampersands before them, are Simulink interface variables. So the code pipes those values in and out of Simulink automatically. You can also create derivatives from these create infos in such cases where you want to have 4 drive motors, but you want them all to have the same settings. These structs live in a constants file for us, but for quick editing and are used in components. This is the entire implementation of a motor set in a component. In the H file, you can make a motor set object with as many motors, create infos, as you want, and then just call these 2 methods in the pre and post step functions, and the library will do the rest. As you can see here, all these motors for the rescape season that aren't serve drive, and we just called 2 methods. It's also very nice because if you want to add another motor, you can just copy paste the create info, edit its values, and add it to the list. Finally, with wrappers, you can see just a small thing that can make a C++ faster. This custom chooser class takes a name for the network tables, the named options and their numeric mappings, and the place the data will go when edited, and all you have to do is paste this in the H file of a component and it'll work.
All right, so what does it look like to develop in a season? So we have, two parts. We have our C++ code, and from season to season, for example, from 24 to 25, there are only about 100 lines of changes that we've made in C++. The majority of our work was in Simulink. And within the Simulink, there are basically three major sections. You have pre-processing, which is signal conditioning and scaling, the game state logic, primarily autonomous logic or teleop, and then post-processing, which could include simple controls or closed loop controls and more complicated things like path following and our swerve control. So basically all of the robot control logic was all done in Simulink. All right, now so I'll talk about student development in Simulink. So Janelyn and I co-developed Swerve Drive before the 2024 season, so that would have been in the summer of 2023. And that was fairly involved. We had a little test robot, and we would develop code and try things out. Janelyn did a lot of research to understand the fundamentals of Swerve Drive and basically coding it up from the bare minimum first principles. And so there was a lot of testing on that little robot and making it all work correctly, and it was working really well. And then Janelyn also developed autonomous path following from, again, this first principles, using theoretical equations for splines, and developed all that logic and the math and the matrix math and all that stuff. So that was done for the first time for the 2024 season. So beyond Janelyn, though, the team did not have programming students available early enough before the 24 and 25 seasons to get them trained, and thus they were not prepared to contribute much to C++ or Simulink code. However, so basically I ended up doing most of the coding for those seasons, but I kept students involved by discussing design decisions, like why we're making certain changes in the code and what this logic is for. Students were very involved in running tests and talking through what needed to be improved based on our testing, and then reviewing code changes together. So I would give them some projects to work on, but then I would end up finishing them in most cases, and then we would review the code changes together to explain, what was done and why. So, but now this summer, in the summer of 2025, we have more engaged students, and we're going through an in-depth preseason training so that students can program in C++ and Simulink before getting to the 2026 season.
So yeah, we should switch to live chat now if everything goes well. See you there. Hi everyone. So this is the follow-up to the presentation. I'm just going to be showing you guys some Simulink code and our C++ code. We're actually going to start with the C++. So, stop simulation. Okay, stopping simulation. So, we have a couple Mac arrows because we have a VS Code extension, Dirt C++ tools. So, I can add a C++ component, and I can do a class name, and you can see it adds a component class. It's all included correctly. It has the right includes, it has the right structure, which is nice. But then if we want to add a motor, what we can do is add motor control code, automatic spark max setup, object name. Okay, so there we go. We have a neoset object. We have the include in there. and we have the two methods added in the right functions. All we need to do now is add in the create info. So let's go to constants and ignore the R stuff. We're going to go ahead and add dirt. We're going to insert motor create info, insert default SparkMax create info, and here we go. We have the default SparkMax create info that's set up. So you can go play around with these configurables until you have what you want. Here is also where you put the pointers to the Simulink interface. So we can do that really quick actually. So if you want to see where that is, it's over here in codegeneral.h under outports. Yeah. So what I can do now, there's a cat near me if you can hear him, is I can grab motor1 DC and go over here, ampersand, code gen model y. Here we go. So we have the outputs and then the port, and now we have everything hooked up. So that's actually it's the wrong pointer, but you get the point that you can. This is kind of the process of adding these pointers in, and then just kind of wires up to Simulink automatically at that point. So we could have an object name here, but we're also just going to pull this over here into our class name.ah, constants, and we're also going to include the constants file. Include constants. Okay, so this should work in a second. Yep. So we've just made all the C++ we need for a motor. All the data will come in automatically, and we could just, this is all we need to do. We also have the DC set up to go out. So pretty nice. We've set up a motor pretty quickly, but I want to get into the Simulink pretty quickly too. So let's get rid of these classes we just made. Includes this, this, and this. This is the auto-generated file by the build script. Pretty small one because it doesn't have a lot of things in the Simulink, but yeah. Pull this one. So anyway, back to this. We have a class called inputs and outputs, a component class. So all it has a motor set here. It also has a gamepad object we're going to be using for testing, because we're going to use the simulation feature in here. And over here we're doing push and pull commands for a motor. We're not going to kick that motor because I'm at home, but we're also going to have this gamepad, codegeneral U, gamepad A. We're going to grab the A button from the gamepad at all times and pipe it into Simulink here. So that's all this. That's all the C++ we have going on here too. So I'm going to go into Simulink here. If you want to see MATLAB, this is the MATLAB file structure we have. But we open the model, and we're in Simulink. This is the top level model. I'm not going to get into what types of models there are, but there are different types, and they do different things, and they have different uses for compatibility of people working the model at the same time. So this is our inside of our top level model. We have our inputs, our outputs, we have our buses here, and then we have our game state logic. So I didn't talk about this a lot in the presentation, but we're going to go into a little bit more here. So here I have the conditional subsystem signals coming into here. So only one of these blocks will be activated at a time. And then all of them have the same signals, same number of signals at least, and that comes into this merge, where these signals are merged with all their like signals from different conditional subsystems here into one signal here. So we're just gonna ignore that these aren't named correctly over here. It's late and I can't fix it right now. So, disabled and autonomous actually don't have anything in them, but we're going to be looking at teleop and test. We're going to go over teleop first. Teleop is a bit much here, but we're going to go over it, and you're going to actually see it's not too complicated. It's just a lot of wires. So, we have gamepad A. We have a detect increase. I'm so sorry. We have a detect increase block, which goes into a switch statement, which is an if statement, but for numbers basically, not like blocks of code, but just a number. And what this, like what I said here, it latches a boolean, but it switches the on or off. It switches the boolean on or off, and it latches on a button press. So it's going to go down and hold this value, because if this is false, which it usually is the rising edge detection, it's going to hold this value in a false loop. But then when you have a true, it's going to take this value, and whatever it is going to output the opposite of it here, which then it's going to hold. So it's just going to do that. It's going to toggle this output here. It's called toggle boolean test point. I have a test point here too. There's also a train. Please ignore that. So here, I have also a test switch statement here for the motor DC. You can have any number here. It's just a constant block. But if this is true, it's going to do this. If it's false, it's going to do this. And that all goes to the motor 1 DC. But what's all this doing? What's all this doing? Well, this doesn't do anything, this part. This just, I'm not going to explain this, but this is just for if we wanted to add test points here. This makes it allows it to, and makes it so that compiler doesn't optimize these ports out. So anyway, this goes in here. So these are all switch statements too. If this is true, it's going to do all the stuff back here. They're all connected here. If it's false to the RGB values, it's going to output 125. The RGB values, I have two options here, 0 or 255. And that all comes from this comparison. So if the input is greater than or equal to 1, it's going to do 0. If it's less than or equal to 1, it's going to go 255 for all of these. And we have some other logic here. So this is kind of similar to what I showed over here with this switch statement with a unit delay on it. Unit delay is, I'm so sorry I didn't explain this. A unit delay is a hold for the next loop block. This signal is going to go here, store for the next loop, and the next loop is going to pull out of here, and then it's going to store a value for the next loop. It just does that over and over again. So same thing we're doing here. We have a starting value in here of 0, and every loop we're going to add t sample to this value, which for us is 0.02. And then we're going to loop back around, and if it's false, which it usually is, we're going to show why, then it's just going to keep holding this value and adding 0.02. Or, if this value is greater than or equal to 2, or something else, then it's going to go true and reset this value back down to 0. So this value is going to be going from 0 to 2 over and over and over again. 2 is actually the number of seconds it takes. So every 2 seconds it's going to reset back to 0. If this value is greater than 1, so if it's 1 second or greater, it's going to switch, this thing's going to be positive, it's going to switch all these to 0. What's this then? Oh, this is kind of this is weird. This is also another detect increase block. This is the toggle we had earlier. So if we go from 0 to 1, if we start this loop here, this on and off of these 0 to 255s, if we start this loop, this is going to go high, which is going to be an OR, so it's going to go OR, true, true, which is going to pull in a 0. So it's going to reset the loop whenever we start looping from 0 to 255. And since 0 is what it sets it to, and 0 is less than 1, it's going to set to 255. So we have basically two cases here after the switch statement. We can have 0 here and 125 for RGB, or we can have a loop with we can have 1 for the motor DC and loop between 0 and 255, starting on 255 every second. That's what this is going to do. So I'm also going to show you in the test subsystem. I have the same logic. It does the same thing, but with different blocks. So this is a chart, a state flow chart, where we have a detect increase block, and we just have a simple little thing here. So this is where we start when we enter the model. We're going to set RGB to 125, all of them, and we're also going to set the motor Z to 0. This is a conditional state transition between states. This is a state, this is a subchart, which is we're going to treat as a state kind of. So if gamepad A is equal to 1, because we have that rising edge detection, if it's equal to 1, we're going to do two things. We're going to have motor DC is equal to 1, and we're going to go into this state, which is actually a subchart with multiple states inside of it. So we've actually done a lot of logic. So we're starting with motor off. We have 125s in the 0. That's half of our equation. And then we have two things happening. So when we go to A, and we go to motor on, we're going to turn the motor on, and we're going to do this. We're going to loop between high and low. High being 255 for RGB, low being 0. And every time we go between these, we're also, because EN means enter. Sorry, I didn't say that. EN means enter. We do this on entry to the state. DU means during. So during, well, every loop, every time we step the model while we have the state active, we're going to increase the timer by T sample. And this conditional transition here is saying every time timer is greater than or equal to 1, we're going to transition back and forth. So it's going to do the same thing. It's going to, every second, it's going to switch between high and low, and 255 and 0. And then whenever we hit gamepad A again, which is when we toggled it last time, but when we hit it again, we're going to exit this subchart and go back to motor off. And I'm going to restart the whole thing. So I'm going to show you this actually works. I'm going to go in and start a simulation. Okay, we're going to use real data station. So we can have our joystick here. So I can show you here. We start with tele-up. So our gamepad A is, you can see every time I hit it, it's going to turn on and off. I'm going to hold it down. So toggle also shows what mode we're in tele-up mode, not in the test mode. So I'm going to toggle on the Boolean. Motor DC is going to be on. RGB is going to switch between 255 and 0 every second. And I can toggle this off, and motor DC is going to go 0, and RGB is going to be 125, which is what we thought was going to happen. So let's go to test. We should see the same thing happen. We're going to start same way in false, so the motor DC is 0. Toggle Boolean won't work because we don't have the test point on in the test subsystem, but I can go here. When motor DC is on, we're going to cycle between 0 and 255 every second, and when it's off, we're doing 125. So yeah, I just wanted to show you guys that it works, and just a little bit of actual showing real life Simulink, and a little bit of how our C++ works here at Dirt. Yeah.